Good morning, everyone, or good time of the day, wherever you are. So we're going to look at Canvas today, and we'll use some commonly used methods, and that's about it. That's how we're going to explore it. Extends, application. So in terms of the boilerplate, you kind of already know it. It's very similar to anything that you would do for any kind of animation, because in order to use Canvas, you typically use animation of some sort. And let's just, the root node doesn't really matter. Use pane. In terms of what we're actually drawing, I don't know. I'll probably just freestyle it. We need typically access to graphics context. So all of these things are more or less trivial. These are the things that you do anyway. As for the actual stuff, we'll have to see. Time start on update, and this thing needs to be extracted to Canvas app. There we go. Right, we need to add our canvas to the pane. We could do that here. Just extract this. That's the only thing that's going to be present in our scene graph. And then we do something with the graphics context in here. So in order to use Canvas, you need to create it. You add it to the scene graph like so, or by any other node, by any other parent. You then obtain this graphics context object, and that is it. Everything else is going to be based on this object called G in this case. You can set fill, you can set stroke. These are two different things in terms of fill is whatever's inside, stroke is whatever's outside of the shape that you're going to then either stroke or you're going to fill. There are a variety of shapes that you can fill in stroke. Right, so what are we actually drawing here? Let's go with particles. You can't go wrong with particles. A particle is going to have, well, the usual x, y, which is the position of the particle. Let's add some color to it. What else? Do we want them to move? I guess so, otherwise it's going to be very static and boring. So let's add a method called update. It's going to do something with x and y. So what are we actually going to do with them? Because I don't want to do sort of like velocity and stuff, because we've already done this many times. First of all, let's create a constructor. I wish I could remember what the hotkey was for creating constructors. Is it Alt Insert? This color. Right. Update. How about we use our cursor to move particles around? But again, I've done this already. Let's do something different. I am going to use something with a cursor, but I don't know what yet. So we'll need two values, mouse X and mouse Y, to keep track of where the cursor is. And we could do that by talking to the scene. if you need any kind of information on clicks, events, key presses, and you want kind of a global handler, then go for scene, because it has all the things that you need. Set mouse moved, I guess. We could add a generic handler, but mouse moved seems fine. We'll just update. Yeah, I guess that'll do. Update our mouse X and Y, so that every time I'm going to move my cursor, these are going to be automatically updated. And since this is being called every frame, it's fine. Before the frame renders, we're going to use these to move our particles around. Now, interestingly, even without moving particles, we can write the code for drawing the particles. Let's have a list of particles called particles. And then we are going to populate the list in here somewhere, maybe even there. So how many particles do we want? What if we do something like this? So we're going to go through each row, then we're going to go through each column. It's too many particles. But we can do something like this. So it's not every pixel that we're covering with a particle, but every 10th. And then every 10th here. It's going to be something like 128 multiplied by 72, whatever that value is, which isn't very big, which is fine. So we can smoothly animate some stuff if we wanted to. New particle, X, Y. X and Y probably need to be multiplied by 10. And then some color. Let's go with blue. First of all, when you're using a canvas, you will need to, on every frame, clear the drawing buffer. So clear a rectangle, and then you provide the dimensions of the rectangle. So something like this, in our case, it's going to clear the entire screen, and then we can draw the next frame. You can also leave this out if you don't want to get interesting effects, because things will be drawn on top of the buffer that you already have. We need to set color, or set fill, I guess, from the color of the particle. Each particle is the same color, so it doesn't make much of a difference anyway. And then fill rectangle, oval, I don't know. Let's go with oval. px, py, and 2 pixels in terms of width and height. Might even do something like this, -1, to kind of offset it so that X and Y are going to be the center of the shape. And that's all the drawing code that we're going to need. Now we need to figure out the logic. Let's just see if this runs. So what I'm expecting is a 2D grid of circles. That's not too bad. This is kind of interesting. So now imagine I'm moving my cursor. Oh, I think I know what should happen. These dots should follow my cursor only if they're within the cursor's attraction distance. So if my cursor is here, bottom right, then anything in the top left is not going to move, just stay where it is. And other points, depending on how close they are to the cursor, they're going to start closing in on the cursor. How about that? That will also use something like a force model, which will allow me to talk about it in a bit more detail. In which case I need to provide cursor's location here. Should I provide it as a data structure or just as raw doubles? I'm going to keep it as point2d because then I can call some methods like figure out the distance between this and these two. So when we're updating each particle, we're going to provide a new point2d, mouse x, mouse y. And just to make sure that we don't generate a lot of garbage, I mean, this is not going to affect our program in any way, but it just feels jarring not to do this. As for why this is kind of bad, if you're thinking millions of particles, this is going to be run that many times. And this will create a new object every time. Although this is a short-lived object, if you're thinking like, if you're running in a game and you have tons of such objects, your heap is going to grow pretty quickly, forcing a GC call, garbage collection call at some point. So you generally try to avoid that, particularly on mobile. Right, so we have this. Let's go for distance. I know we're going to use distance, but I don't know how we're going to use distance. I think we need a maximum distance, a minimum distance, and something in between. So the closer you are to the cursor from the particle point of view, then the force that attracts you to the cursor is greater. I think that's what should happen. Which means small distance, big force. Big distance, small force. So it's inverse proportional kind of thing. Yeah, that makes sense. I'll just run the algorithm through my head and it works. So hopefully this will work in sort of real implementation. Max distance, max attraction distance, attract distance, something like that. So how big is our window? Let's go half of this, 360, maybe 350. Actually, let's use doubles. And this is min attract distance, which I guess something like this. Because if your distance is less than that, then it should really be just that. Like you automatically teleport to the cursor's location. Which means we have if, else if, else. So if the distance is greater than the max distance, then we do nothing. No, we set the particle's location to the original, because imagine this particle would have been moved at some point, and if we don't do anything, it'll just stay there, and we want it to go back to its original location. So original x is what we want to keep track of. Also, if distance is less than minimum, then x is essentially this thing, cursor's position. And then else, that means it's anywhere in between those two distances, anywhere in that range. And this is where it gets interesting. So I'm thinking of a force model, something like a constant multiplied by 1 over x, x being the distance, so 1 over d. Force models exist in physics and also in graph theory when you're trying to, say, visualize a graph. And the model essentially tells you what forces are being applied to each of the nodes. So if you're thinking in graph theory purposes, which is, I think, a much easier representation than in physics, you have a graph. A graph is a collection of nodes with a collection of edges. So nodes are kind of like points, and then edges are the lines that connect these points. So this is a graph with 3 nodes and 2 edges in between. In order to visualize such a graph, because they can get complex, like if you're visualizing Twitter network, you can have millions of connections, right? And in order to visualize this in an aesthetically pleasing way, is the term, you can use one of the force models available, or you can come up with your own. And what it does, it tells you what forces are being applied to each node. And ultimately, then you run the simulation and it moves the nodes around, and you end up with an interesting looking image. So I'm trying to do something similar here, but in a very simplified way. So I'm just going to use something like this, I think. Use the constant factor. So I'm going to extract it here. Static final double force factor, force constant. I don't know what that value should be, so I'm just going to arbitrarily put 5, and we'll adjust it as needed. And then this will tell us the force being applied to each particle. There's only one force, which simplifies the whole thing. So there's just one force vector, which is from the particle to the cursor. Which means I can do something like this. So imagine the star is a particle, and this x is my cursor. So there is a force being applied that way, from the particle to the cursor. So what I need to do is figure out what the vector is, which should be trivial. I just take cursor, subtract x and y. In order to get a vector, you take 2 points, and we do have 2 points, so this is point 1, this is point 2. A vector goes from point 1 to point 2 if you go 2 minus 1. So this, which is cursor position, minus that position, which is x and y, give us this vector, which goes from here to here. I don't want the full force of that vector, or the full length of the vector, because otherwise it's just going to move my particle to the cursor's location. Not ideal. I want it to be somewhere along the line. So we need to scale the vector down, and that scaled length, I think, can be determined by using this formula. Scaled length is our, what do we call it? Force constant multiplied by 1 over the distance. because if the distance is big, then the attraction is small. If the distance is small, the attraction is big, which is why it's 1 over something. We can now obtain the scaled vector, so we can take this original vector, which is the distance between 2 points, and we can scale it. So we can do something like this, right? We're scaling it down because we don't want the entire length. To do that, we normalize it, which brings it to a unit vector, and then we multiply it by the scaled length to achieve the length that we want. All we do now is basically add the vector to the original point, which is to the original point, not the current. So it's original plus this. Something like that. We might need to play around with the force constant and possibly even with the formula. We need to run this and see how this works. There is some movement, but it's tiny. So we need to increase the force constant. Right, so the distance is between these two values, which means maximum distance is something like 349. So if this force constant is 349, then the whole value is 1, which is, it's 1 pixel. It's not going to be great, so we need to make this super big. Whoa. That looks awesome. You have a mesh, kind of. And this is somewhat similar to how you would do, I think, spring mesh it's called in physics, where things kind of move closer as you drag them, but there's also damping and other physics properties that you need to add. This is a very simplified model that I've chosen to use. This looks mesmerizing, almost. I think that's it. I can't really top that in this video. We can play around with values, but that's about it. If you want, you can change the background to something interesting. And alternatively, you could also make some changes to how the particles actually move, because currently we're just teleporting them to the location. What you could do is move them smoothly over time, and you might get a very nice effect, I think. Anyway, I think that's all done. So we've looked at the canvas and some of its methods that you might use for various purposes, like if you want to draw particles, if you want to have game objects or such, I don't know. You can draw images with draw image function. And the common workflow with the canvas is you obtain the graphics context, you clear it every frame before drawing, and then you draw your game state or whatever it is that you're trying to visualize with the canvas. These bits are kind of a boilerplate, which is why it's quite common to see these, because you do need to construct a canvas You do need to have a timer going so that it calls you back every frame. And then since it's the only thing in the scene graph, it doesn't really matter what kind of parent you use to add it to the scene graph. And here's a little tip for getting mouse X and Y positions if you want to be able to do something with them. Right, that's it, folks. I'll see you guys in the next video.